Okay, wrong thing. It's a good thing there wasn't anything bad in there. Okay, can you see the right screen now?
Yeah.
Yes.
Okay, good. Okay, so we have glucose and fructose, right? So each of these corners represents a carbon, and you have that carbon that's also up here. So do me a favor, count how many corners this guy has. That would have a carbon. That has an oxygen there. And then I want you to count the oxygens.
6 corners.
There's 6 corners. Okay, so there's 1, 2, 3, 4, 5. Well, don't count the one with the oxygen in it. So just count the ones that just have nothing in them, those corners.
Okay.
And then add the total number of carbons, because that's an additional carbon up here. So, and then that's the same thing with this guy here with the fructose. And then I want you to count the number of oxygens. And then I'll just give you the number of hydrogens. So I want C, H's, and O's. Here, C, H's. Oops. Okay, how many carbons did you guys get?
Two? No, wait.
Was it just one?
1.
You only got 1 carbon? Now, are you listening to what I'm asking you to do? Okay, I'll tell you one more time. I want you to count. So this corner here, where it says 5, that's a carbon. That's a carbon. That's a carbon. So every corner represents a carbon. You're going to count those as a carbon.
5.
And then you're also going to count the one that's up here. So there's a total of how many? 6. Okay. What about over here? Same concept.
4, 5.
And what about this one here?
7.
Count it again.
1.
There's 1, there's 2, there's 3, there's 4, there's 5, there's 6. Okay. Each empty corner, where if there's not a letter there, that's going to be a carbon. Okay. So now if we counted our hydrogens, I'm going to just put those down for you. There's 12 of them. I'll explain to you how you count those later on. There's 12 of them over here. And now count the oxygens for me. 1, 2, 3. How many oxygens did you get? Let's see. Abel. How many oxygens do we have?
Do you count just the O's or the ones with the oxygen and hydrogen?
Count just the one that just count O's only. O's.
1.
Well, not I should say count all the O's.
Oh, okay. So it would be 4 and 5?
5.
Are you sure?
1. Oh, 5.
5.
Are you sure?
3, 4, 6. 1, 2, 3, 4, 5, 6.
Are you sure?
Yeah.
Okay, it is 6. Now what about this one here?
1, 2, 6.
Okay, so Are these chemicals the same?
Yes.
Yes.
They are? Do they look the same to you?
No.
Formula is the same.
The formula is the same, but are they the same?
No.
No, they're not the same. These are two different chemicals. One is glucose, one is fructose. Fructose is primarily found in fruit, fructose. Glucose, as I told you, is often found in beets, right? So both of these are sugars, but they are slightly different from each other. What is the difference that you guys see?
The structure.
Their structure. One has a 6-ring structure. 1, 2, 3, 4, 5, 6. 6 called the ring because it
5.
closes up on itself. Yeah. And one has a 5-ring structure. Okay, so they're going to behave differently. They're going to taste differently. They're going to react differently. For instance, fructose takes more energy to break down than glucose, right, in our body. So it takes more energy for us to break down fructose than it does to break down glucose. Okay. So that's why they're always telling you to eat fruit, right? Because it takes more energy to break down that sugar so that you can use it for energy, right? So then you're not just getting fat. It's not just being stored in your body, right? Okay?
Yes.
So these guys are called isomers of each other. Same chemical formula, but different chemical structure. Okay? We good?
Yes.
Okay. Good, good. Okay, so this is an example of an isomer. It's real simple. Now let's talk about resonance structures. Not what I wanted. All the wrong things are popping up today. So a resonance structure is so they're going to be 2 or more equivalent Lewis dot structures. The only thing that's going to be different about them is that we're actually changing where those electrons are located. Now, let me give you a concrete example because it's really hard to look at it without actually seeing it, okay? Or understand it without actually seeing it. So let me give you our example here. So we have, these are my 3 Lewis dot structures. This is oxygen 1, this is oxygen 2, this is oxygen 3. This is oxygen 1, 2, 3. Okay, Diana, can you tell me the difference between the A structure and the B structure? Are you there, Diana? Diana. I guess she left. Let's see, Osman, can you tell me the difference between the A structure and the B structure?
The oxygen has a double bond with the S.
But don't they all have double bonds with the S?
Well, it just changed. Well, like it's changed. It depends, like where it's at, I guess.
Oh, okay. So in A, it's on the 3rd oxygen, and in B, it's on the 2nd oxygen. that what you're saying?
Right. Yeah.
Okay. Stephanie, can you tell me the difference between B and the C structure? You there, Stephanie? Vanessa. There's two of you guys, so one of you guys should answer, right? Are you there, Vanessa?
So oxygen 2 is has a double bond, and then in the C it has a double bond in oxygen 1.
Okay. Okay, so these are examples of resonance structures. The only thing that's changing between these structures are your electrons are moving, right? So my electrons here in A are in that double bond location. But in B, I've moved them double bond location to the second oxygen, right? So it forms a double bond. This guy moves here, this guy would form your double bond. So it's just the movement of electrons that is really going on. So we're moving electrons. So we have three different structures because the double bond is moving from one oxygen to the other oxygen. Okay, so this is an example of resonance structure. Now, if I had something like this, let's go.
No, I have a question.
Okay.
If they're all like different, are they all still correct?
That's where we're getting to right now.
Okay.
Okay. So we have structures A, B, and C, right? Which one of these are resonance structures of each other, and which one of these are isomers?
A and C are resonance structures, and A and B aren't. And C and B aren't.
Okay. So A and C are resonance structures of each other. Okay, because all we're doing is moving the electron from one oxygen to another oxygen. A and B, or B and C, are isomers of each other. because in this case, we have a different structure. So that double bond being on the S is a different structure than the double bond being on the O. But chemically, they're exactly the same chemical formula, right?
Yes.
So we would expect these guys to behave differently because we have a double bond on the S compared to having a double bond on the O. So they're going to have different properties as well. So does that help you? Did that answer your question?
Are those A and B's from the first ones we did or the second
No,
ones?
the second one, the blue A and B's.
Okay.
So we'll say up here. The first A and B's, these guys, the pink A and B's, these guys are all resonant structures of each other because they're only O's. Bless you.
Thank you.
Can you explain that one more time?
Sure.
So is it pretty much if the they're isomers, if it all depends if the bonds switch between the
If
Oh.
it, yeah, so if the bonds are switching between two of the same element type, if they're both O's, right? And you're just moving one bond, it's a single bond here and it's a double bond there. That's going to be a resonance structure, right? If they're just switching between these two. So we have A and C, right? Double bond on that oxygen that's going down and double bond on the oxygen to the side here. Okay. So we're switching where the double bond is at, but it's the same element. That's going to be a resonance. But if I have a double bond on the S,
It's switching elements.
it's switching elements.
Okay.
That's going to be an example of an isomer, right? That's one example of an isomer. Okay?
Okay.
Okay. So simple, you'll be able to give me the answer to that on test,
Hopefully.
hopefully.
I'm not sure. I'm still a little bit confused.
Okay, what is it that you're confused about?
Well, like, I still don't get how, like, all of the bottom ones are the same, like resonance structures.
Okay, tell me something. The elements that are attached to the S, are they different from each other? On the bottom ones, on the pink ones?
No. Or,
No.
well, yeah.
They are?
Well,
How are
they
they
all
different?
have different.
Are they different elements? I'm asking you, are they different elements? What is an element?
Oh, no, they're not.
They're not. Okay, so this is one of the things. We got to make sure that we understand the terminology. So they're not different elements. So they're all the same elements, right? So what are we doing differently between A, B, and C? Pink A, pink B, and pink C.
The bonds.
The bonds. We're moving the bonds, right? Which means that we're moving electrons, because electrons control our bonds, right? So the difference between A, B, and C that are in the pink is that we're moving electrons to form bonds in different spots. The elements are exactly the same, right? So that is called a resonance structure. Just the movement of those electrons between the exact same element, resonance structure, okay?
Okay.
Now, isomer is when you have, like up top where we have the blue A, B, and C. I should have, let me use different letters. Okay, so if we're looking at E, F, and G, which ones are resonance structures of each other?
Sorry, what did you say?
I said if we're looking at E, F, and G, which ones are resonance structures of each other?
A or E and G.
E and G, because that's where the electrons are being moved. We're moving from one oxygen to another oxygen. So E and G are going to be resonance structures of each other. Now, E and F, because we're going from a double bond on an S, in the case of F, to a double bond on an O. Now that is an isomer because they're different elements.
Oh.
Okay?
Okay.
So these guys are two different structures. Although the chemical formula, if we write the chemical formula, it will be written TeSO2, right? Chemical formula for this guy is also going to be written TeSO2. If we didn't draw the Lewis dot structure of it, we wouldn't know that they were different from each other, would we?
No.
No, we wouldn't. So we needed that structure to sit there and distinguish it. So often these guys are going to have two different names associated with it as well, so that to help us understand that there's a distinction. Okay.
Okay.
Kind of like, remember, glucose and fructose, right? Two different names, but the chemical formulas are the same and the structures are different.
Okay.
Okay.
Thank you.
Okay, so electron pair geometry. So now this is going to start being bread and butter. So we need to understand that we need to draw these structures and how these structures kind of play on each other. So we also need to understand that we've been drawing our Lewis dot structures. Well, these structures have geometry associated with it. What kind of dictates the geometry are the number of electron pairs that we have available, right? That are free. You guys know that electron pairs are lone pair electrons are what? Are they part of bonding or are they not part of bonding?
Lone pairs are not part of bonding.
They're not part of bonding, okay? So, but they're going to play a part in how that structure is going to be, how the pairs are going to interact with the other pairs, how they're going to interact with the bonds. So the way it works is electrons are going to try to be as far away as possible, right? So if you have two electron pairs in an atom, they're going to try to be as far away as possible as they can be from each other. And also, they're also going to want to try to be as far away as possible they can be from an attachment, an attachment to an element or something like that. So you want to try to get as much space between you and the other guy, right? So if you're connected, where am I? Okay, so can you guys see my hand?
Yeah.
And my glow sticks? Okay, so that's one glow stick. This is another glow stick. My hand represents the center atom. The glow sticks at the end of the glow stick is another atom. So if I had two attachments, they're going to want to try to be as far away as possible from each other. So if this is hydrogen and this is hydrogen, right? And we'll say we have oxygen in the middle. Well, we can't use oxygen. We'll use beryllium, right? We have beryllium in the middle. So this is beryllium, this oxygen, and this oxygen. They're not going to want to be like this right next to each other. They want to take as much space as they can take away from each other. So the angle for this guy is what? Do you guys remember geometry?
Sort of.
What is the angle of a circle? Completely all the way around.
360.
360. Yes. So 360. So from here to here should be
180.
180. So this guy would be a linear structure, and it's 180 would be the bond angle. So from here to here, the angle would be 180. We're going to try to be as far away as possible from each other, okay? Now, if I have 3 of these guys, so if I have 3 of these guys, my bond angle is going to be what?
90?
90? So 360 divided by 3, is that 90?
No.
90 would be like this.
Mm.
So that would be
120.
120,
120.
yes. So it's going to be 120. Okay? Because I have 3 attachments, it's going to be 120. Okay? And they want to be as far away as it could possibly be. Now, if I add one more, and this is all we're going to get to, although there's others. Right? So if I have 4 things, now, yeah, you would think it would be 90. But what's going to happen is, because this guy is going to, it's a 3-dimensional structure, really, and it wants to get as far away as it can possibly get from each other, 90 isn't far enough. It's going to go to 109. So this will be 109, this will be 109, this will be 109, this will be 109. This here is 109, this here is 109. It'll be 109, it'll form a 3D structure. This guy here looks like your jack. Did you guys ever play jacks when you were in school?
Yeah.
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 So you remember that how that jack looked? It has 4 sides, right? And that structure is called tetrahedron, right? Or we say tetrahedral. It's a tetrahedral structure. Okay, so the geometry would be tetrahedral, 4-sided structure, because it has 4 attachments, 1, 2, 3, 4. Each of these angles are going to be 109. Okay? So let me show you. Okay, the first one. How many attachments do we have?
2.
We have 2. So the bond angle is 180. So what are we going to call that structure? What's going to be the geometry of that structure?
Can you repeat that again?
What will be the geometry of this structure? The first one, A.
The first one.
Linear. That's right. Okay, because just 2 attachments, right? Forms a line straight across. 180 is our angle. It's linear. Okay. What about this guy? This guy has 3 attachments. This guy is going to be called Trigonal Planar.
That's a weird name.
Why is it a weird name? Tri, 3, gonal, right? So 3 sides, and planar, meaning it's all in the same plane, right? So it's flat. It's not bent anyway or anything like that. It's all flat in the same plane. Trigonal planar. Okay? Now the fourth one, I already gave you the name. Let's see if you guys remembered it. If I have 4 attachments, 1, 2, 3, 4, what is it called?
Tetrahedron.
Okay. So, but we call it tetrahedral when we're talking about the geometry. So it's a tetrahedral structure. Okay. Okay, so now those electron pairs, those lone pairs play a part in this, right? So we have what we call our electron pair geometry. That means that we're taking into account the electron pair as well as the attachment of atoms. Okay, so if I have the pink here, you guys see the pink? You see the pink?
Yes.
You see the green?
Yeah.
Okay. So if I have 2 pink and 2 green, right? Each lone pair, so the lone pair is represented by the pink, the green represents an atom, okay? And this is my center atom. My fist is my center atom. So what is this structure? What would be the geometry of this structure?
Tetrahedral?
Tetrahedral. If I have 3 lone pair and 1 atom, what would be the geometry of this structure? Or attachments again. The only thing, these are lone pairs.
Tetrahedral?
Tetrahedral. If I have 2 lone pairs and 1 attachment,
Trigon.
trigonal what?
Plane.
Planar, that's right, trigonal planar. Okay. If I had 1 lone pair and 1 attachment,
Linear.
okay. Okay. Simple so far?
Yeah.
Good. Oops. Okay, so now let's look at these balloons. So what would be the the electron pair geometry for these 2 balloons? That
Linear.
represents our center atom in the middle. What did you say?
Linear.
Linear. What would be the bond angle?
180.
180. What about this guy?
Trigonal planar.
Trigonal planar. And the bond angle?
120.
Okay. And this guy?
Tetrahedral.
Tetrahedral.
Hedral.
And the bond angle?
109.5.
109.5. Simple?
Yeah.
Okay. Okay, so let's make it a little more complicated.
Um,
Oh, God.
Okay, so you guys are familiar with the electron pair geometry. That's when we're taking our electrons and the attachments that it has, the other atoms that it's attached to in consideration to kind of get an idea of what it's supposed to look like, right? So, but what happens in reality, we have what we call molecular geometry, what the molecule looks like. So in the case of the molecule, the electrons affect it. Those electron pairs affect how it looks, but we don't see them. So then it'll have a different shape than what we think it is. So for instance, we'll start off simple and then we'll build up. If I have BeF2. Well, BeF2 is going to have B in the middle, Be in the middle, F on both sides. So it's going to look something like this. My fist is the Be. These guys represents the fluorines. So what is that shape?
linear.
Linear. Simple, not too hard, right?
Yeah.
Okay. So if I have B, F3, that's going to look like this. Okay, now my fist is B. Each of the green glow sticks are an F. What is that going to look like?
Trigonal planar.
Trigonal planar. Okay, so if I have something like this, SO2, well, this guy is going to look like this. Okay, so my hand is the sulfur. The green now represents the oxygen, each of the oxygens, and then the top represents a lone pair. The pink represents a lone pair. Okay, so what is the electron pair geometry? How many attachments all together with the electrons, electron pair, each of the oxygens? How many different attachments do I have?
3.
3. So what would be the electron pair geometry?
Trigonal planar.
Trigonal planar, okay? Now the molecular geometry, we don't see the electron pair, but it keeps that same shape as if you do see it, right? So, but now this guy looks like what? It's considered to be linear because it's not straight across. It's bent. The angle here is going to be about 120, right? Because it's as if we have that electron pair, 120, 120, 120, but you don't see that attachment up top. So this guy is called bent or angular.
But it is still trigonal planar.
The electron pair geometry
Right.
is trigonal planar, but
Okay.
the molecular geometry is bent
Okay.
or angular. You see the difference? You see what I'm,
Yeah.
okay? So this guy is bent for its molecular geometry. Okay, so for our next one, say CH4, that looks like this. So we have 4 attachments. Okay, so I have my 4 attachments. So what is my electron pair geometry?
Tetrahedral.
Tetrahedral. And what is my molecular geometry?
Tetrahedral.
Tetrahedral. Okay, so let's say I had this guy. So this is ammonia. Okay, my lone pair is in pink. And each of these are hydrogens, and my fist is nitrogen.
Bent
Okay.
or angular.
So what is the electron pair geometry?
Tetrahedral.
Tetrahedral. So as soon as I look at the molecular geometry, we have 3 sides, so that's called trigonal, and it looks like a pyramid. Does it not look like a pyramid?
Yeah.
Okay, so it's called trigonal pyramidal. Okay, so the molecular geometry would be trigonal pyramidal. Okay, So in the last case, we have water, H2O. So oxygen has two lone pairs up top, or two lone pairs. So it's like this. So what is the electron pair geometry?
Tetrahedron.
Tetrahedral. And then what is the molecular geometry?
Bent or angular?
Bent or angular. Okay? Do you guys get that?
Yeah.
Okay. Piece of cake so far?
Yeah.
Good. Okay. Let's see. Okay, so we have methane. So what is the electron pair geometry? I'm going to write down on here. EP, EPG, electron pair geometry. For the first one, A.
Tetrahedral.
What is the molecular pair? I mean, the molecular geometry.
Tetrahedron.
Okay. Okay, what about for ammonia here in the middle, B?
Tetrahedron.
Okay. So the electron pair geometry is tetrahedral. And the molecular geometry?
Trigonal pyramidal.
Trigonal pyramidal, that's right. And then in the case of water, it's EPG,
Tetrahedral.
tetrahedral. And its molecular geometry?
Bent
Or angular.
or angular.
Okay. Okay, piece of cake?
Yeah.
So far.
Good.
Is the screen blue or is it just mine? Oh, there it
No,
is. Okay.
I was blocking out
Oh,
the
okay.
answers. So, yeah. Okay. Okay, so because we want to know what things look like, and we know that things are three-dimensional, we also need to find ways of drawing it. And one of the ways of drawing a three-dimensional structure is by using what we call the wedge dash diagram. Okay, so the way that works is, better just to show you. Okay, here we go. Okay, so you guys see our figure, NCl3, right? So you guys know what it looks like in terms of its Lewis dot structure. It's going to be like this. Okay, the way that we would draw it with a wedge dash structure, on your phone, you guys have the how good of a signal you guys are getting, your Wi-Fi signal or your cell phone signal,
Yeah.
your bars. Something like that on your phone, right?
Yeah.
Okay, so that's what that is, right? So that means that that chlorine is going towards the back, okay? The big line, that means the chlorine is going towards the front. the straight line means that the chlorine is going towards the side. So you have one in the front, one in the back, and one on the side. Okay, you guys see that? Front. Back. And side. Okay, front, back, and side. Okay. And then you had your other one up there, so that would be like your top, your lone pair, but we don't see that. Okay. So we draw it to help us understand where things are going to be located. That's going to be our back, that's going to be our front, and that's going to be the side. So you should be able to draw that if I ask you to. Okay.
Okay.
So how would this guy look? So somebody draw that for me, since I failed it. So I don't know if you want me to draw it. Okay, I'll pick somebody since nobody's going to volunteer. Let's see, who are we gonna- Xavier. Are you there, Xavier?
I have a Chrome, so I can't.
Oh, you can't
annotate.
draw? Okay, Kevin.
No.
Are you there, Kevin?
I have Chrome, so I can't.
Are you lying to me?
No.
Okay.
There you go, Alberto. He's
All
volunteer.
right, Alberto. Thank you. He's quick too. Alberto is a Zoom expert. Good job, Alberto. Okay, questions, concerns, Cash? Good. So if it's trigonal planar, am I gonna have to put, does it have to be three-dimensional? Trigonal planar. Do I need to put something in the front or the back?
No.
No. So in that case, there's not going to be any three dimensions. So if you can do me a favor, if I look at a molecule that has more than one center atom, right? So I have to look at the geometry of each one independently. So I'll draw my Lewis dot structure, and then I want to draw my three-dimensional structure looking at each one independently. Okay. So for instance, here, C2F4. What is that going to look like? What is going to be the molecular geometry of each of the center atoms?
Tetrahedral?
Are you sure? So first thing that you want to do is draw the Lewis structure. So what does the Lewis structure look like for this compound?
The two C's in the middle and then the F's on the outside.
Two C's in the middle.
And there's two bonds between C.
So a double bond.
Yeah.
So we want to call it a double bond because a double bond is different than two bonds. Like the F here and that C, those are two bonds. A double bond means that they're sharing. Okay, so like this. This is what you're telling me. Okay, so what would be the molecular geometry of the first carbon? How many attachments does it have?
2. So
Three.
Trigonal planar.
trigonal planar.
Trigonal planar because there has 3 attachments. 1,
Uh,
2, 3, because it's attached to the other C, right?
Right.
And then what about the second C?
The
Same
same.
thing.
The same thing. So in this case, would I have would I have a wedge diagram, a wedge dash diagram?
Yes.
No, because there's no back inside to it.
Yeah, there's no back and side to it. It's all trigonal planar. It's all on the same plane, so it's flat. So I would just draw it this way. That's it. Okay. So where each of these angles are 120. Okay.
What would the electron pair geometry be for the sun?
The electron pair geometry would for the C's, because you look at your center atoms. So what do you think it's going to be? Are there any lone pairs?
For
Are you there?
sorry, yes. For C, no, but for fluorine, yes.
Yeah, but we're looking at the center atom, right? Fluorine isn't the center atom. So the center atom is going to determine your molecular geometry. It's also going to determine your electron pair geometry as well, right? Because if you notice, we've always had center atoms. So in that case, what's going to happen? If we're looking just at that C,
It's going to be trigonal planar as well.
okay? And if we're looking at the other C,
It's also going to be trigonal planar as well.
yep. Okay. But that was a good question. Okay. Okay, so now let's talk about polarity. Okay, so a molecule is going to be considered to be asymmetrical if you have uneven distribution of charges. So it's symmetrical if the distribution is evenly distributed, right? So so do you guys remember when you calculated your bond, your electronegativity? It's also called your bond polarity. So if we wanted to determine who's being favored, where is that electron going? Are they sharing it evenly or are they sharing it unevenly? Is it polar or isn't it polar? You guys remember calculating that? How do we do that? How do we calculate bond polarity?
Don't we need that one periodic table that gives us the
electronegativity?
Yeah,
Yep.
of each.
Yep. So we want our electronegativity table, right? So we know that these guys, carbon and hydrogen, was considered to be nonpolar. So that means that they're sharing evenly, roughly. So these guys are all sharing evenly, okay? So if they're all sharing evenly, each one of these, that means that nobody's pulling stronger than the other, okay? So if nobody's pulling stronger than the other, the molecular polarity is also going to be symmetrical in this case, because it's all being pulled evenly on all sides. So that would be symmetrical. You guys understand that?
Yeah.
Okay. So if I have C in the middle again, and I have Cl, Cl, Cl. If we calculated the bond polarity of just C and Cl, if we looked at it all by itself, Cl is more electronegative than C. And there's a difference so that it favors the electron is going to want to go to Cl more. It's going to be at Cl side more than it's going to be on the carbon side. And so that's going to happen in all 4 cases, right? So let's say Sandra was dating 4 guys and they were quadruplets, right? They're all the same. They looked exactly the same. They're all 4 of them were gorgeous, right? Right? So Sandra is spending the same amount of time with each of the boys, right? So are any of them going to pull Sandra's heart more than the other, or is it going to be exactly the same? They're exactly the same.
Exactly the same.
It's going to be exactly the same, right? So in that case, the pull is going to be evenly distributed, right? So then that means it's going to be symmetrical. And it's also going to be nonpolar. Nonpolar meaning that no side is favored. Even though the bond, each individual bond was polar, you're getting pulled evenly on all sides. It's going to be nonpolar. Can you guys see that?
Yeah.
Okay. So now we're going to take a look. I'm going to give you a couple of scenarios. Let me get there. Okay. So here we have Sandra in the middle. The 4 guys, right? All exactly the same, look exactly the same, have the same amount of money, everything, okay? So she's going to share evenly with all of them. She's going to date all 4 of them as long as she can date all 4 of them, right? Okay? So the next scenario, we replace one of those hot guys, right? That same amount of money, same type of attitude with the deadbeat, crackhead, okay? So the hydrogen, this is represented by the white, deadbeat, crackhead, all the yellow guys, right? Those are the gorgeous guys, have money, they all look alike, they're strong, right? Crackhead, weak, no money, deadbeat. So who's going to be spending, who is Sandra going to be spending more time with in this case?
Not the crackhead.
She's going to spend less time with the crackhead, and she's going to be spending the majority of her time between the 3 guys. So that time that she would waste on that crackhead, she's not going to do it. She's going to go ahead and use it on the 3, right? So it's going to be favoring the chlorines, right? So is that polar or non-polar in terms of molecular
Polar.
polarity? Polar. Because she's favoring someone. Is it symmetrical or asymmetrical?
Asymmetrical.
Asymmetrical. Because the crackhead doesn't get the attention, right?
Mm-hmm.
Okay. So in the case of this scenario where we have 2 hydrogens and we have 2 chlorines, 2 crackheads, 2 hot guys with money and everything going for them. So who is Sandra going to spend more time with?
The 2 hot guys.
The 2 hot guys, right? So in that case, the dipole moment is going towards the two hot guys. And these guys, the crackheads, don't get any attention or get minimal attention. So in this case, is it asymmetrical? Is somebody being favored over others?
Yeah.
Okay. So it's asymmetrical. Is it polar?
Yeah.
Okay. In this scenario, so Sandra has 3 crackheads, 1 hot guy. Right? So chlorine again, hot guy. Okay. So who's going to be favored under these circumstances?
The one guy.
That one guy. So polar? Yes or
Yeah.
no?
And asymmetrical?
Polar and asymmetrical. Okay. I think it's spelled right. I think I spelled it 3 different ways, 3 different times. Okay. Now this last scenario, 4 crackheads. So is she gonna want to spend time with any of them?
No.
No, not really. So she's gonna keep it to herself, right? So in that situation, it's still even pull on all sides, gonna be all the same. It's gonna be non-polar, right? Because nobody gets any attention.
And symmetrical?
So, and it would be symmetrical. Yep. So it'll be polar and symmetrical. Oops.
Wouldn't it be non-polar?
Non-polar?
All right. Thank you. Non-polar. Good job. I was testing you. Good job. Okay. Simple.
Yes.
Okay. Okay. So under these circumstances here, this is very similar to what we talked about earlier. We have carbon in the middle, and each of the red ones are oxygen, right? Who is more electronegative, carbon or oxygen?
Oxygen.
Oxygen. So if we looked at just the bonds, right, the oxygens would be polar, correct?
Yes.
Okay. But since I have 2 hot guys pulling me both ways, then what's going to happen?
Non-polar?
Going to be nonpolar. So the molecule is going to be nonpolar, even though that individual bonds were polar, right? So the molecular polarity would be nonpolar. Would this be symmetrical or asymmetrical?
Symmetrical.
Symmetrical.
Okay. Now, in this case, oxygen is more electronegative compared to hydrogen. This is hydrogen,
Polar?
oxygen, hydrogen. Yes, and you're right, it's going to be polar, right? So each bond is also going to be polar. So in this case, oxygen is like taking it for itself. It's like, I'm thinking about me, so it's going to be more polar. So like you said, polar, the molecule's polar. Is it symmetrical or asymmetrical?
Asymmetrical?
Okay, piece of cake.
Yeah.
Good. Kimberly, are you there?
Yes.
Okay, you get it?
Yeah, I get it.
Okay. Okay. So, let's see. Oh, Vivian, are you there?
Yes.
Okay, Vivian and Xavier. Since Xavier couldn't draw, we're gonna make him talk. So, Xavier, tell me your definition of organic.
Organic, that it's like natural, not man-made.
Okay. Vivian, what is your definition of organic?
Well, I was thinking the same thing.
You were thinking the same thing? Okay.
Yeah, like that's the first thing in my head, like natural, I feel like.
Okay, so I'm going to tell you guys, throw that definition out the window. So let me give you my definition of organic. Okay. So, and the chemist's definition of organic. Organic is anything that has carbon in it. Okay. So pesticide, organic. Drugs, organic. Food, organic.
Anything with carbon?
Anything that has carbon in it. Okay. Now there are a few exceptions, and most people that say that there are exceptions are not organic chemists, right? They're typically inorganic chemists because they want to try to claim a little bit of carbon in their life, right? So the exceptions that you'll hear occasionally will be carbonate, cyanide, oxide carbons, and I'll give you examples of those here in a second. But everything else is considered to be organic that has carbon in it. Now, and for the most part, if you talk to an organic chemist says anything that has carbon in it is organic, okay? So carbonate, you guys use baking soda? Baking soda.
Yes.
Okay. Baking soda is sodium bicarbonate. The chemical structure for sodium bicarbonate is CO3 NaHCO3. That's the structure for sodium bicarbonate. Now, sodium bicarbonate would be considered, if you talk to an organic chemist says sodium bicarbonate is organic. Right? If you talk to an inorganic chemist would say sodium bicarbonate is inorganic because it only has one carbon. Right? But we have methane. Methane only has one carbon in it. It's considered to be organic by both of them. Okay, so the inorganic chemists, they get picky, and all that stuff. But for the most part, anything that has carbon in it is gonna be organic. Okay, we're good there?
Yes.
Okay,
Yeah.
okay. So who was it? Who's the other schmo that has a Chromebook and couldn't draw? Who was that? Was that Kevin? Are you there, Kevin?
Yeah.
Oh, okay, Kevin. So I have a question for you. Okay, Kevin, I want you to think hard. Think real hard. Okay? So, what do you think hydrocarbons are?
Organic?
They are organic because they have what?
Carbon?
Carbon. So what do you think the definition of a hydrocarbon is? Jack, I'm going to pick on Jack. I haven't heard anything from Jack. Jack, what do you think hydrocarbons, the definition of hydrocarbons is? Are you there, Jack? Hector?
Jack's here.
Jack's here?
said I don't know if he is.
Well, I see him here, but I mean, you know, he's probably playing video games or watching his telenovelas or Sports Center.
Maybe he's in the
Hector,
bathroom.
or maybe he's in the bath. That is a possibility. He could be in the bathroom too. Hector, are you there?
Yes.
Okay, Hector, you're gonna help me out. Hydrocarbons.
Hydrocarbons. Well, it was a question.
Yep. What is the definition of hydrocarbons?
Hydrocarbons.
Hydrocarbons. Think about it. Hydrocarbons. What was that?
Hydrogen. Hydrogen.
Hydrogen, yes. Hydrogen and
Carbons.
carbons. Good job. Yes. So hydrocarbons are hydrogens and carbons. So if you have something that just has hydrogen and carbon in it, it's called a hydrocarbon. And we know because Kevin just told us, and I'm sure Jack would have told us if Jack was listening and not in the bathroom, right? He would have told us that it's organic, right? Yeah, no, maybe?
Yes.
Okay. So I'm going to put chemicals on the board, and I want you to help me out here. So we have, okay. So which one of these are hydrocarbons?
Is the first one?
Okay. So the first one,
Second one.
okay. So we have the first one,
The
Third
next one.
Fourth one.
The fourth, fifth, and
so you said the fourth,
fifth and sixth.
Uh-huh.
so this is what you're telling me right now.
Yeah.
Everybody agree? Anybody disagree? That's incorrect. Hydrocarbon has only what?
Carbon and hydrogen.
Hydrogen and carbon.
Hydrogen and carbon. Do the last three, I mean the last two, have hydrogen and carbon and only hydrogen and carbon?
No.
No.
No. Okay, so that's, these guys are not hydrocarbons. Are they organic?
Yeah.
Yes.
Yeah.
Okay.
They have
So
carbon.
these are organic. Anyone else organic?
CSO, CH, and CH2.
All except SO4.
Okay. And who's inorganic?
Oh, four.
SO4.
And so forth.
Okay, piece of cake.
Yeah.
Mm-hmm.
Good. Okay. Let's see, we have 10 minutes. Okay, so let's talk about these hydrocarbons. So we have three major families of hydrocarbons. We have what we call the alkanes. So Diana, inorganic is anything that doesn't have carbon in it. So if it doesn't have carbon in it, it's considered to be inorganic. And as I said, inorganic chemists, they will sometimes say things like carbonates are inorganic or cyanides because they only have that one carbon. Okay, but if you talk to an organic chemist says, no, we claim that. So, okay, inorganic, not organic. That's what it means. Okay. Alkanes. Alkanes are saturated with carbons. That basically means that you only have single bonds with your carbons and your hydrogens. So for instance, if I have C, H4, this guy is called an alkane. Okay, this guy, its name is methane. If I have CH6, all single bonds, this guy is called methane. Okay, so do you see anything that's similar between the name alkane and methane and ethane?
Yeah,
The last part?
the aim.
The ane, right?
Yes.
Okay. So what do you think this front part is going to tell us?
It only has single bonds.
Or is that the last part? The last part tells me it's only has single bonds, right? The A and E. Because that's what alkane is. It means anything that a hydrocarbon that only has single bonds. So what do you think the first part tells me? So this part here, the meth and the eth.
Is it the element structure?
What is the difference between
Number of carbons.
number of carbons, right? Okay, so this prefix, meth, means I have one carbon. Eth means I have two carbons. Prop means I have three carbons. Bute means I have four carbons. Pent, what do you guys think that means?
5.
What do you think the next one is going to be?
6.
Hex.
6? Hex. And 7? Hept. Most people don't know 7.
Oct.
Oct. Known is 9. Dec is 10. Undec 11. Dodec is 12. Okay. Questions, concerns, Cash? Okay, so if I have a carbon structure that has 2, 4, all single bonds. What is that structure going to be? What is going to be its name?
Thing.
Thing.
Would it be heptane?
Heptane. Simple?
Yeah.
Okay, good.
Yeah.
So, as chemists, and also just as scientists, we're lazy. We don't like to write if we don't have to write. And writing out all those C's are such a pain in the butt, right? So if the write 11 C's by the time I'm finished, it's tomorrow, right? So I need to find a quick way of doing it. The way that we do that is we use points or points and lines. So one, two, three, four, five, six, seven. So this structure here, I would just draw as a line that starts 1, 2, 3, 4, 5, 6, 7. Each point represents a carbon. And then we know that it's single bonds, so we're going to saturate it. Carbon can only have 4 attachments. So there's going to be 3 at the end. We understand that there's 3 at the end. And then each of the middle carbons are going to have 2. Okay? And 3 at the end. So to keep from having to write all of our H's, since we know that everything is going to be a single bond, all I have to do is put the number of carbons I have there, and we understand that we're going to saturate it with hydrogens. Okay? Saturation meaning it just has hydrogens on it. Okay? Have you guys heard of saturated fat?
Yeah.
So saturated fats only have single bonds. They're carbons with only single bonds, and they're saturated with hydrogens. Okay. Unsaturated fat has double bonds. And then we have the next family, which has double bonds called alkenes. So that means that it's carbons that could have at least one double bond. So if I have this guy, and this is my double bond in that stick figure, what would this guy be called? How many carbons do I have? Let's count the points.
6.
A hex.
2, 4, 5, 6. So it would be called, you said, hexene. That's right. Okay. And then there's another family.
Triple bond.
If it has a triple bond. And usually, let me draw this correct so you guys can see it the way it really should be. So a triple bond always is going to end up being linear, right? So then the carbon here, so you have, this will be your first carbon. That's your second carbon. This is your third carbon, and this is your fourth carbon. So this guy would be called, and the family is alkynes. That would be the family name. So what do you guys think this guy will be called?
But
The time?
How many carbons do I have? I heard somebody say but what?
butane. Time.
Butane. So butane, yes.
Oh.
Yeah, it's pronounced bute, but butane. That's correct. Butane. Although butane sounds so much better though. Okay, so oops. Okay, so if they're all single bonds, they belong to what family?
Wait, what was that?
If they're all single bonds, they belong to what family?
Oh,
Alkyne.
alkane.
Alkane. Ane. If
Oh.
they're all triple bonds, they all belong to what family?
Alkyne.
Alkyne. And then if they're all double bonds, they belong to what family?
Alkene.
Alkene. Okay? You guys got that so far?
Wait, can you repeat that?
I sure can. If they're all single bonds, they belong to what family?
Alkane.
Alkane. A and E. If they're all double bonds, or if they have at least one double bond, then they belong to what family?
Alkene.
Alkene. If they have at least one triple bond, they belong to what family?
Alkyne.
Alkyne. Y and E. Okay? Okay. So I think this is a good stopping point.